All right, so this is covering 5.3, which is Poisson distribution, probability distribution. So what we're going to do is we're going to cover a couple questions from this section that's been asked. So number 3 asks, a Poisson probability distribution says the random variable x represents the number of phone calls the author receives in a day. And it has a Poisson distribution with a mean of 7.2 calls. What is the possible values of x? And then also asks, is x equal to 2.3 possible? Is x a discrete random variable or a continuous random variable? All right, so to answer the question is, we have a couple different properties of a Poisson distribution, and I'll even kind of show you what's written in the book. So this is the requirements for Poisson distribution. We'll describe the formula as well. So the requirement says it's a random variable x. This is the number of occurrences of an event in some interval. The occurrences must be random, and the occurrences must be independent of each other. Also, the occurrences must be uniformly distributed over the interval being used. So the idea is you're not supposed to get, like if you're talking about phone calls over the day, you're not supposed to get like 50 of them in like that first 20 minutes and then basically none of them or very few of them after that. So what they want is they want them somewhat uniformly distributed. And if it is random, it tends to be, uniformly distributed anyway. Now, what we have is our formula for our distribution. Just like with our binomial formula, we had a p of x formula. The binomial formula was, again, choose x times p to the x times q to the n minus x. But the formula for Poisson distribution, for finding like the probability of exactly x happening, happens to be mu to the x, e to the minus mu, all over x factorial, where mu represents the mean. E is a number similar to pi. Pi is an irrational number, 3.14159, blah, blah, blah. It keeps going on forever. E is also an irrational number. It's 2.71828, and it goes on forever as well, so it's an irrational number. There's actually a button in your calculator that's an E button. And while we're at it, we can kind of show you where that E button is right now. So if you see your LN button, the blue button that sits above it is your E button. So if you hit your second button and then hit that LN button, what you'll see is you'll get E out. And since E is an exponential base, the next thing that you plug in, so if like we have a mean of what it said before in that problem, I think it was 7.1. Yeah, 7.2. Then you'd have to the minus 7.2 because that's what the formula like would call for, like e to the minus mu. Of course, we're missing these two pieces, but we'll get there in a second, okay? Okay, so this is how we find that. Now your mean is it's the mean number of occurrences of an event in the interval. So really, what you kind of do is it's like the number of occurrences divided by your interval is how we do that. Now sometimes the book actually gives you the mean, and sometimes you have to calculate the mean. So in problem number 4, they actually gave you the mean. So problem number 3, they actually gave you the mean. All right, what also makes a Poisson distribution a little different than a binomial distribution is a binomial distribution would have a fixed number of trials. So, n would be equal to like 8, or n would be equal to 10, and no higher. But a Poisson distribution, your random variable x, your discrete random variable x, can actually go on forever. So if you ask how many phone calls could you get in a day, there really is no upper bound. You could get 10, you could get 15, you could get 20, you could get 100, you could get 1,000. We really don't know that upper bound, and technically it can go on forever. Now the probability of you getting 1,000 phone calls in that particular day, so if you did try to like create a probability distribution table, just like we can do with, just like in section 1 where we have this probability distribution table, you could get 0 phone calls in a day, or 1 phone call, or 2 phone calls, or 3 phone calls, or 4 or 5, and so on. With the Poisson distribution, this random variable x, this discrete random variable x, can go on forever because there is no real upper bound. Now the way you find that p of x again is it's mu to the x times e to the minus mu all over x factorial. So that's how that's calculated instead. And then of course you can actually build your list this way. Now you can never really complete the table because this goes on forever, but as you get higher and higher and higher, eventually that probability is going to go lower and lower and lower. Like if you were able to graph this, like if this was the x-axis and this was your y-axis, your Poisson distributions kind of have they have a shape that kind of looks like this, kind of skewed way to the right. Okay. So as you can see, as like, the mean, they said it was about 7.2. It's going to be pretty close to the, to the top of this, but it's going to be pulled over because it's skewed a little bit. So 7.2 will probably live right there. So, whatever the probability of 7.2 is will be that number. But as you get, well, to tell you the truth, you can't really have a 7.2. You can only have 7. The mean being 7.2 doesn't mean you're going to get 7.2 calls that day. It just means that that's the mean number. So, you could have 7 and you could have 8 calls and you could have 9 calls and you could have 10 calls and so on. But as you go further and further out, you can see that these probabilities are getting smaller and smaller and smaller and smaller and smaller and smaller. So that's kind of the idea. All right, so back to the question again. I keep going, trying to explain that Poisson distribution really well, and then we can actually go through the examples a little quicker. So, all right, so what's the possible values of x? Well, since x can go on forever and forever and ever, x is actually infinite. It's countably infinite because it can be 0, 1, 2, 3, 4, and forever. But it is infinite. Can the value of x be 2.3? Well, it can't. You can either get 1 call or 2 calls or 3 calls or 4 calls, but it can't be 2.3 calls. Now I know you see a mean of 7.2 calls, but that just means where that arithmetic mean is actually going to land. So it's going to land somewhere between 7 and 8, but closer to 7 is kind of the idea. So if you looked at that, if you're going to do all the boxes for each one of these, what you'll notice is that the box around 7 and 8 will actually be bigger than all the other boxes. So like these heights, these probabilities will actually drop off. So that's why it kind of looks like that skewed right bell-shaped distribution. Is it discrete? Yes. It's a discrete because these things are countable. So that was number 4. Possible x is infinite. X equals 2.3 is not possible. And is a discrete, and it's discrete. All right. Oh, yeah, discrete. All right, so let's answer a question. Let's do, say, like number 7. And I'll explain where they get these numbers as well. So number 7 says, in 5 through 8, assume a Poisson distribution, and assume that the mean number of Atlantic hurricanes for the United States is 6.1 hurricanes per year, as an example 1. And I'll go back to example 1, and I'll show you how they got that 6.1, because in the problems over here, you're going to have to calculate that mean. All right, so number 6 says, find the probability that in that year there are, let's do number 8. I want to add a number. Say, find the probability that in that year there is exactly 4 hurricanes. All right, so going back to example 1, I want to know how they got that 6.1, in case we have to calculate this later. What we have for the mean is the mean number of occurrences of the event in the intervals is it's the number of occurrences divided by the interval. So what you'll see is a mean is actually, in this section, a ratio. So 8. So if I want to find the mean, it's the number of occurrences divided by your interval. So what we noticed in exercise 1 is that in a 55-year period, there were 336 Atlantic hurricanes. So this is the occurrences, and this is your interval. So you know that it's going to be equal to 336 divided by 55. So this is going to be hurricanes, and this is going to be years. So when you divide this, you actually get what's called like a unit factor. You're going to say how many hurricanes there is per year. That's really what this means. So, it's a mean of 6.1. So if you divide that 6.1 hurricanes per 1 year. Per 1 year. You don't really have to say the 1 here, but just to kind of reinforce that, it's going to be useful when we answer letter C. All right. So it says find the probability in that year there's going to be 4 hurricanes. So what we know is that for A, we know that P of X is equal to mu to the x times e to the minus mu all over x factorial. So when we set this up, if I want P of exactly 4, P of 4, now remember, now we know mu and we know x, so we can plug everything in. Remember, e is a constant, so it's just going to stay the same. So I'm going to have 6.1 raised to the 4 times e to the minus 6.1 all over 4 factorial. And let's calculate that. I'll show you how it's done on the calculator. It's, no parentheses are needed. It's actually really convenient. So when you turn it on, you have 6.1 raised to the 4. Pull it out of the exponent by pressing the arrow key over. And you're going to have times your E button, which you hit your second button, and then you hit this LN button right here. And that's going to give you your E. You can see that. You're going to raise to the minus. Make sure when you do negatives that you're using this negative key and not the subtraction key. It'll give you an error. So negative 6.1. Pull it out of there, and then divide by, it says 4 factorial. So you can hit 4, go to math, over to probability. So over to probability, and then down to factorial. Then hit enter. So what I get is this value is 3 sig figs is going to be 0.129. Now I'm going to write a couple more in here, just because a lot of times when they ask you to calculate some other answers, when they're calculating them, they actually use this number, even though when I ask you guys to do this on a test, when you're done doing this on a test, when I ask you for the mean, you're going to go to this is a probability, so you're going to go to 3 sig figs. But I'm going to use this when answering the questions because I went around last, not first, okay? So now it says, in a 55-year period, how many years are expected to have 4 hurricanes? So that's part B. So remember, this is the probability of 4 hurricanes happening in a single year. So if you want to know how it's going to happen over 55 years, you just take this number and then you multiply it by 55. So you know your expected number of hurricanes in 55 years is going to be so number of the expected number of, I apologize, that doesn't make sense. The expected number of years with 4 hurricanes, exactly 4 hurricanes, over a 55-year period is, so what you're going to do is you're going to take your 55 and then multiply it by P of 4. We can tell kind of like this expected number is kind of very similar to finding like the mean of a binomial distribution. You know, it's n times p, so that's kind of your expected number. It's kind of from that idea. So this is going to be 55 times this 0.129. So let's see how many we have. 55 times 0.129. So we get about 7.1. Now remember, this is the number of hurricanes, and they gave hurricanes per year 6.1. So since this is the 6.1, I'm going to go 1 decimal past our basically. I lied. X is your random variable, so X is integers. You can have 1, 2, 3, 4, 5 hurricanes. So I'm going to go 1 decimal past X. So this is going to be equal to 7.1. So 7.1 hurricane. 7.1 years of the 55 that you're going to have exactly 4 hurricanes. And what they said is, how does the result from Part B compare to the recent 55-year period in which 10 years actually had 4 hurricanes? Well, what I calculated from a Poisson distribution is about 7.1 years is going to have exactly 4 hurricanes. Well, they said the actual number is 10. And to be honest, 7 is pretty close to 10. It's not bad. It's actually okay. Now, the reason why we do stuff like this is because, you know, we need to have some kind of funds for like hurricane relief, and we need to know how many hurricanes are possible to happen. So you know, the probability of having 4 hurricanes, you know, is 12.9%. So then you could also calculate 5 hurricanes and 6 hurricanes and 7 hurricanes. So you can actually save like what's the probability of having 4 or more hurricanes. So you can kind of have a rainy day fund to at least be able to fund, you know, relief for that particular situation. Let's do another one. Tell you what, I'm going to expand this problem. I want to describe this a little bit more. This is the answer to it. This is like clean and easy. But what I want to do is I want to create a probability distribution and kind of show you what a Poisson distribution actually looks like. So this is just going to be number 8 expanded. So we can kind of talk about this. So we know that a Poisson distribution, or all probability distributions, it can be set up as a table. So x and then p of x. And then our random variable is going to be 0 and 1 and 2 and 3 and 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. That's probably enough. Remember, this goes on forever. But what's going to happen is your probability is going to peak somewhere around the mean, and the mean is 6.1, so your probability is going to peak around the 6.1, and then it's going to drop off later. So I kind of want to show you that. Now remember that p to the x is going to be equal to, it's mu to the x times e to the minus mu, all over x factorial. And what we know in this situation is that the mean is 6.1. And then our x, if we're going to use our table, is going to be L1 times e to the minus 6.1 all over L1 factorial. Because I'm going to have my calculator generate these numbers, and then we can kind of show how that works. So stats, I'm going to go to edit. I'm going to clear out this stuff that we did. So what I'm going to do is I'm going to go all the way down to, let's see, 11, 12, 13, 14. This might be overkill, but go down sufficiently far until these probabilities get small. So then I'm going to go over to L2, press up and hit enter, and I'm going to put in a formula just like we did with the binomial, except I'm going to use this formula here. So what I have is 6.1 raised to the 4 times e to the minus 6.1. Where's my L1? Did I mess it up? Let's see. Not raised to the 4. X is actually L1, so second L1. Times 6.4, 6.1. Let me make sure I say this again because it wasn't clear. So remember, it's 6.1 raised to the L1, which is what we have here. Then it's going to be e to the minus 6.1. And then after we're done putting this in, I'm going to divide by L1 factorial. So second L1, and then I'm going to go to math, go over to probability, pop in factorial. And what's going to do is it's going to generate all the probabilities for you. Now remember, we've already calculated P of 4, which is right here, 0.129. So we know that we did it right because we've already calculated that. So pop in these numbers in, just kind of write them out. I got 0.002224. This is 0.0137. I'm going 3 sig figs. 0.0417. 0.0849. The P of 4, what we already calculated, but it's still 1.29. P of 5 is 0.158. 0.160. P of 7. 0.13, yeah, 1389, so I have to go with 140. 0.107. Hopefully these things start getting small. There we go. You can see that they're starting to drop off. Maybe I'll put some more numbers in there so I can just show you. Unfortunately, when you put numbers back in there, you're going to have to, I'm not going to write them all down, but I'll show you this in a second. So I'm going to go back over here. I have to redo the formula if I want to populate those. So enter, clear this out. So 6.1 raised to the L1 times second natural log to the minus 6.1. Make sure that you're using this negative key here, okay? 6.1 divided by second number 1, math, probability, factorial. So when we pop those things in, we can see our numbers. Let me just calculate it. Let me go through and finish this list. So 9 is going to be 0.0723, 10 is 0.0441, 0.0245, 0.0124, 0.00583, 14 is 0.00254, 0.006, 0.0103, and you can see like 16, 17, see how they're dropping off. So that's 15 and 16. We'll just do this the last one, 0.00039, and as you can tell, they're getting smaller.
Surprised to see you here.
I have an online class as well, and I know that like 5.3 is due for them this weekend. So
Oh, yeah.
I want to put the video up there. It's actually I'm going to put it up for your class as well.
Cool.
So you guys can have a look. And at least you can get working on it this weekend. But
Right.
I figured if I'm going to make it due, they should probably.
5.2, so it's 5152.
That's due. That's right. Yeah. But for them, it's 515253.
Wow, they're ahead.
By one section, and we'll catch up to them next week. It'll be fine.
Okay.
I just don't want to. I don't want to give them like 6 things that are due next week for them. So if I just, they only have 3 sections due.
Wow.
They finally caught up to you guys. They were a little bit behind, but
Oh, and then that's kind of surprising.
well, they move at different speeds. Like you guys, I can kind of tell the speed of the class just by looking at you guys and seeing and looking at your questions. But an online class, you know, it's more self-paced.
Yeah.
So what I do is I just do it evenly. So I make them do like 4 sections a day. But for you guys, like I front load the easy stuff and try to slow down on the hard stuff. But
Yeah.
but I try to.
So it's better. I mean, look at you. You're curating it to be better suited for us.
I'm trying. Like I said, I do the best I can. But you know, it is what it is.
Yeah.
Hey, let me finish this. I got to get home though.
Oh, I'm sorry.
No, you're good. I don't mind.
I just saw you. I was like, oh my God. I'm surprised to see
I
you.
always appreciate it. Like I said, I don't mind talking, but I want to finish it because I got to get my daughter to dance class.
Oh, well, good luck on that.
Thanks, buddy. Have a good one.
You too.
So, okay. All right. So, okay. So what we notice is that these things are going down. And again, if you look at it like this, you can kind of tell these are the x-axis, and you can tell that it actually kind of peaks, and it peaks right around what you'd expect. It peaks at, remember it was 6.1, right? You notice your probabilities, the highest probabilities are right here, aren't they? Now the reason why, you know, I know that that one's higher than this one, but since this thing tails off, since what we have is something that looks like this, that skewed right is going to take what you'd expect the mean, which my bad. So when you look at the picture, you kind of expect the mean to be the highest number, but it's technically not. Remember, you're adding up all the numbers and essentially dividing by how many there are. And since you have a lot more numbers over here, it's going to take this peak and actually it's going to slide it over a little bit. So even though, you know, this thing is your, you know, this thing right here would be your, you know, your number 6. And then over here would be your number 7, and so on, as far as your heights. The reason why it's 6.1 again is because the skewed right's going to pull that mean over to the right just a little bit. Again, this is a probability distribution, so you know this is numerical. And if you did calculate more of them, you could probably do it now. If you added these numbers up, even though I didn't get all of them, if you added all those numbers up, they're going to add to 1. So even though it's infinite, the addition of all those numbers are going to add to 1 because eventually these things are basically going to become 0. So if you add up like the first 20 of them in this particular example, it'll be equal to 1. Maybe other examples you might have to add the first 100. But that's really what a Poisson distribution is. It's a probability distribution where this random variable x, your discrete random variable x, is infinite. All right, one more question. So what we're going to do is number 14. So number 14 says disease cluster, and it's relevant to to you know where people live. So the idea says neuroblastoma is a rare cancer. It occurs in 11 children in a million. So the probability of that is 0.000011. So what they did is they did 11 divided by a million, and that's how you get that. Okay. So 4 cases of neuroblastoma occurred in Oak Park, Illinois, in which there's only 12,429 students. Now we know that only 1 in a million this happens to, right? So we're kind of asking ourselves, this is kind of the idea, is 4 cases out of, you know, like just 12,000 children seems like an anomaly. But we want to make sure, because, you know, there's going to be fluctuations that can go up and down. Is 4 really an anomaly? So this whole goal right here is to basically see if it is an anomaly. So in order to do that, the very first thing it asks us to do is it says, assume this neuroblastoma occurs as usual and find the mean number of cases in the groups with 12,429 children. So what they're asking for is they're really asking for an expected number. So the way you find an expected number is you take your n and then you multiply it by your probability. So the expected number is going to be A, the mean for this particular case, or your expected number, is equal to it's going to be your 12,000. I'm way out of frame here. Here we go. It's going to be 12,429 multiplied by the probability, which is 0.123411. So what we're going to get here is 12,429 times 0.0000. Okay. So what I get is I get 0.13. I'm not going to round this because I want the answer to be more accurate, but we will, like, the answer on a test is going to be equal to 0.137. But when I calculate the rest of these things, I'm going to use this number because I don't want to round now. I'd rather round later, okay? All right, so now we have to be a little careful. We have to read this because usually when you use the mean, your mu is this number right here because it is 11 out of a million. But in this case, they said use the unrounded mean from part 1. So now what we're doing is we're saying this is equal to mu. So now they're calling this mu for the situation, that mean. So it says use the unrounded mean from part A to find the probability that the number of neuroblastoma cases in the group of 12,429 children is 0 or is 1. So what they want to know is they want to know the probability of that. So what we know is that, again, P of x is equal to mu to the x times e to the minus mu all over x factorial. But in this case, they're saying let mu be equal to 0.136719. And then in this case, and they want x equals 0 and x equals 1. So P of 0 is going to be equal to 0.136719 times x, which is 0, times e to the minus 0.136719. all over 0 factorial. And then P of 1 is going to be equal to the same things, except we're just going to have 1 instead of 0, 0.136719 times e to the minus 0.136719 all over 1 factorial. And then I'm just going to calculate them. And you've seen me do it enough, so popping that in, we have 0.136719 raised to the, I forgot to put 1 up here. Raised to the 0 times second e to the minus 0.136719 pull out the exponent divided by 0 math probably factorial. Enter. Does that make sense? Okay, I think so. Just want to make sure I didn't mess it up. Just a second. And let's do it for 1 as well. 1. Just what I'm doing is I'm just changing the zeros to 1s now. The way you do that is you hit the second and enter button and it'll just replace the formula you had before. Okay, so what I get is this one is equal to 0.87. I'm just going to round to 3 sig figs, and 0.119. So that means P of 0 or 1, or means addition, so 0.82 plus 0.119. So I'm going to add these two numbers, so go up here, this plus up this. So what I get is I get 0.991. All right, we're almost there. So what is the probability of more than one case of neuroblastoma? So what they want to know is what's the probability of more than one? So the probability of 2, probability of 3, plus probability of 4. So in order to answer that, is I want to kind of talk about, remember that this is a probability distribution. So we know that P of 0, so for C, P of 0 plus P of 1 plus P of 2 plus P of 3 plus P of 4 plus P of 5 plus, remember these are infinite. So if you add up all the probabilities, since it's a probability distribution, it needs to be equal to 1. And like I said, you could test that. I did that with the previous section. You could test those things to add them up and actually see if you get 1. So when they ask what's the probability of, so they're asking for what's the probability of more than 1. What they're actually asking for is they want to know the probability of 2 plus 3 plus 4 plus 5 all the way to this. So if I want to find that probability, what I'm going to do is I'm going to subtract those things from 1. So to solve for this red thing, just subtract those off. So that means this should be equal to 1 minus p of 0 minus p of 1. Because remember, this red right here is equal to this, right? For the same exact thing. That's 1 or more. That's more than 1. That's more than 1. So when I solve for this box right here, which is this box, you just subtract off those two numbers. So what I'm really going to do is I'm going to subtract off this number right here, because subtract that, so it means I'm going to subtract this, so this is going to be 1 minus 0.872 minus 0.119, which is the same thing as just subtracting that, so 1 minus 0.991, 1 minus this number, I can't believe I use my calculator here, but this gives you 0. I went through 6 things, so 0.0854, so that's what we get. So that's what we get. All right. So the probability of getting 1 or more people with this neuroblastoma is less than 1%. It's less than 1%. So remember what we talked about as far as tails go. Like if you're looking at you really want to know that if you live in like in the usual values, if your number is significantly high or significantly low. So if you add up all the probabilities, and this number right here might be 2. What we know is that area, probability of 2 and 3 and 4 and 5. So if you're adding up all that area, that probability is 0.00854. And since this number is less than 5%, that means it's beyond this tail, because there's got to be a tail here, whatever it is, to where the rest of this is going to be 95% of the data, right? And if you're outside the 95% of the data, then that means you're in this tail of unusually high. So if this is 95%, that means whatever's here would have to be 5%, right? 0.05. And since this number is less than 5%, that means this 2 and also the 3 and actually the 4 and the 5 and so on, these are all significantly high numbers. So that really comes down to that 4. Like, should 4 happen? Actually, if you try to calculate the probability of 4 or more, you're going to even notice that number is going to be even much smaller. So the fact that like they shouldn't have 4 people, that basically means there's probably some cancer-causing agent in there that's biasing them. They're not the normal population, so there's some kind of thing affecting them. And that's it for 5.3.